In the previous lecture, we talked about dual pairs, and we talked about a particular way to form a dual pair, basically taking the linear programming relaxation and then taking the dual of that linear program. But we should emphasize that dual pairs can be anything, and in particular, we can have two integer programs that are dual pairs with one another, and there's no taking a dual in between. To do that, we'll go through a particular example of dual pairs where the idea is more combinatorial than taking a particular process, like taking a dual. The first program we're going to work with, or the first combinatorial problem we're going to work with, is the vertex cover problem, which we might be familiar with. Our input is going to be a graph, and the objective is to find some subset, C, of vertices, so that every edge is covered. That is, for every edge, either U or V is going to be in my cover. And this set C is the minimum such set that's going to achieve this goal. Over here in our graph, we can see what a particular vertex cover looks like. Here our graph has a couple of nodes and a couple of edges. The nodes highlighted in blue form a cover because for every edge, one endpoint of that edge is going to be in the cover. So for example, if we look at this edge, one side of it is covered by this blue vertex. And that's true for every edge, so this forms a cover. We've seen how to formulate the vertex cover problem as an integer program. This integer program is to minimize all the vertices that we choose, subject to the constraint that for every edge, at least one of its endpoints is chosen, and each one of these vertices is either 0 or 1. For purposes of our discussion here, we're going to call the optimal solution of this program ZCG. That is, we're given a graph G, and we'd like to compute some number for that graph, the cover number. The cover number is Z superscript C. The dual problem we're going to introduce is the matching problem. In this problem, we're again given a graph, but now our objective is to choose a matching. A matching is a subset of edges so that no edge in M shares the same vertex. That is, two edges don't touch one another. And we'd like to find the matching M that's the maximum set of edges. So in this graph over here, we have an example of a matching, these two pink edges. We can see that these two pink edges don't share any of the vertices. And for example, if we were to add an edge, say this green edge, to our matching, it would violate the matching constraint. That is, this green edge touches an endpoint of one of our pink edges, so it can't be included. We can formulate the matching problem also as an integer program. In this case, we're out to maximize the edges, so now there's a variable for every edge. And we write a constraint that for every vertex, at most one edge of our matching can touch it. Every edge can be chosen or not, and so these XE variables take the value 0 or 1. For purposes of our discussion, we're going to call the optimal solution to this Z superscript M of G. That is, we take a graph and we compute its matching number, which is Z superscript M. This is going to give us the value of the maximum matching inside of this graph. We'd like to show that these two problems, the matching problem and the cover problem, form a weak dual pair. To do that, we need to show that for any matching and for any cover in the same graph G, that the size of the matching is going to be a lower bound on the size of our cover. Or alternatively, the size of our cover is going to be an upper bound on the size of our matching. So we'll pick a particular matching M. And we can write out what M is. M is going to be a set of edges. Let's say V1, V2, V3, V4, all the way up to VK minus 1 to VK. And because this is a matching, none of these vertices are going to touch one another. That is, none of these edges are going to touch one another. So each one of these vertices is distinct. So V1 through VK are distinct vertices. Our cover, C, on the other hand, is going to cover the entire graph, but in particular, it's going to cover this matching, which is a subset of all the edges of the graph. And because it covers every edge, each edge that we see in our matching has to have at least one of its endpoints inside of our cover. So for the edge V1, V2, either V1 is in C or V2 is in C. And this is true for all of our edges. So either VK plus 1 is in C or VK is in C. Because all of these V's are distinct, we can conclude that for every edge in our matching, we have at least one vertex in our cover. That is, if we look at the size of our cover, just to cover the edges in the matching, we have to have at least one vertex, so we have to have at least the number of edges in the matching in our cover. This is our final conclusion. And because C and M are the objective function values of our matching problem and our cover problem, these two problems form a weak dual pair. You'll see that the proof that this is a weak dual pair is very combinatorial in nature. And this isn't going to be out of the ordinary. Whenever we come up with a dual pair, occasionally they're going to be combinatorial. And to prove that they form a weak dual pair, we'll have to go through a very combinatorial type argument.